Hi, welcome to our talk on Spark Diagnostics. So I'm Chris, and I'm a software engineer here at Databricks, working on Spark, mostly on Spark SQL related topics. So in the past, I've also worked on a couple of JVM implementations. I have with me Chung, who is also a software engineer here at Databricks. He's a Spark PMC and also a Parquet committer. Switching over to Chung.
Okay, thanks, Chris, for the introduction. Hi, everybody. This is Chen. So I'm super glad to be able to see all of you here. So Databricks provides a unified data analytics platform for accelerating innovation across data science, data engineering, and business analytics. So a lot of innovations are recently happening inside the Spark community. We are very excited to provide a solution for our customers around Apache Spark, Delta Lake, MLflow, and projects like Koalas to simplify everybody's daily workflow.
Distributed applications are hard. You can hit all the issues that would happen local to a single node, plus a lot more. Distributed applications are inherently hard to develop, to tune, and to diagnose. And various factors contribute to this. When it comes to diagnostics, one of the biggest hurdles is that useful information may be scattered around or simply lost. And you need to follow the breadcrumbs to gradually discover how the dots are connected. At Databricks, millions of clusters consisting of tens of millions of instances are being launched every month to host our customers' workloads. While it's exciting, this is also a perfect environment for bugs to lurk in either our customers or in our own platform. This talk brings you some of the lessons that we've learned and case studies from our real-life bug hunting experiences.
Thank you, Chris. So one of the common issues you can hit is performance regression. So performance regression shows some symptoms like a query runs slower when you switch to a newer Spark version, or sometimes you are still using the same Spark version, but there are some characteristics of your underlying data changed, and you still observe some performance regression. And at this time, the most intuitive thing you can do is to check the Spark SQL query plan by running an explain command. So if you observe that the query plan changes before and after you switch in the Spark version or you switch the underlying data, then the regression may likely be from an Catalyst optimizer change or because the Catalyst optimizer tries to choose a new plan according to the characteristics of your underlying data. This may change. The second case may happen when, for example, the data volume changes and the Catalyst decided to use a different kind of joins or try to change the join order. And if the query plan stayed the same before and after the change, then the regression could be coming from various sources like query optimization and compilation delays or task scheduling delays, or even network operations and the JVM GC issues. So a few tools and the methodologies that we can use here is firstly, you may want to build a benchmark so that you can reproduce the performance regression. And in this case, usually you want to minimize your benchmark so that you can reproduce that as fast as possible. But sometimes this is not feasible, but that is still okay. After you are having a benchmark, usually we want to attach a profiler to your benchmark to record some traces and profiling data for afterward analysis. So here is the real case we hit during Spark 2.4 development. Inside Databricks, we have a benchmark team who does performance sign-off for Databricks runtime releases. So Databricks runtime is a proprietary fork of Apache Spark inside Databricks with a better performance and other extensions. So in the 5.0 beta version, we had found a significant performance regression versus DBR 4.3. And multiple TBCDS queries were slower. And one of the example is a query 67. So the tool we are using here is a flame graph and async profiler. So one of the key skill you might want to master while debugging a distributed application is that you want to try to reduce the multi-node distributed application issue into a single node issue. And the async profiler is one of the such tools that you can leverage. So by recording execution of the one executor side, we can sample the execution traces of the JVM process, and then we can produce such a flame graph. And we want to, usually we want to record at least two flame graphs. One is before the change, and one is after the change. And you can see that these two flame graphs changed slightly. And those changed parts are usually where the bugs are lurking. So now here we are zooming to the difference in the hotspot. And the figure above is the one produced from a DBR 4.3, which is a good version. And the image below is the one produced from 5.0 beta. And you can see that there are some differences between these two images. So the key difference here is that while doing an aggregation, the good version, DBR 4.3, is doing a hot loop calling monomorphic function. And in this way, we are avoiding extra buffer copies. While in the newer version, 5.0 beta, this code path got changed and is calling a polymorphic function instead. And an extra buffer copy is introduced so that the whole aggregation process is a lot slower. Next, I'm gonna share another kind of issue that happens commonly, which is a job ham. So the symptom of job hams is quite annoying. Sometimes you can observe that one job finishes very fast for the first 90% or 95% of the whole progress. However, for the last 5%, maybe just one or two tasks, it is stuck there almost forever. So here are some tools and methodologies that you can leverage. First of all, thread dump from the Spark UI is always very useful because when you are hitting a job ham, usually you are hitting a deadlock or some threads are busy doing something not useful. And in that case, you can observe them from the thread dump. And also, there can be network issues. And maybe your Spark job is actually contacting some remote resources or services, for example, reading from S3 or Azure Blob Storage. And the third tool is that sometimes you might need to do some JVM debugging so that you can do some, you can dig for some low-level details. And the last one, which is very interesting, is about the log exploration and visualization. And using this, we can often find some interesting insights about the whole distributed application from a global view. So the first case study I'm going to share is a shuffle fetch on the data executor that causes entire cluster ham. So quoting from the report from our customer, saying that the customer found there are a lot of exceptions in the Spark log. Something like an RPC timeout exception. We cannot receive any reply from some places in 120 seconds. And during about the same time, about a 10 minutes gap, when the exceptions happened, the entire cluster and the customer complained that in this pretty large cluster, the cluster usage is extremely low. And here are some early triage questions. During when it crossed a hand there, are there anything special happening before the cluster hand? And that thing might be the root cause of the hand. And when the cluster hand there, is there anything happening during the hand? So is it completely silent, or is it busy doing something? During such a cluster hand, sometimes a deadlock happens and executors are just being silent there, or sometimes they are just busy doing something unuseful and burning the CPU for no good. So in order to answer these questions, we can use a few tools. And the first one is the Spark History Server, where you can check event visualizations of executors, the jobs, the stages, and tasks. And the second one, inside Databricks, we use the Spark logs in Delta Lake. So within Databricks, we have an ETL pipeline that extracts Spark logs into Delta tables for fast exploration. And of course, all these are with the consent of our customers. The interactive notebook environment is also very essential to leverage Delta Lake for interactive log exploration and visualization. So from the Spark UI, we can see that one executor got removed right before the cluster hand, and another new executor was added, and that is also about the same time the cluster hand stopped. So one thing we want to try to see is that one thing we can try to determine whether a node is active or not is to check the logs this node is producing during a certain period. So here we are checking the time period where including the whole cluster hand and 2 minutes after the cluster hand. So as you can see, using this query, we're checking a specific time range, and we are only checking the Spark driver node. And we also aggregate on a per minute basis to check the number of total log messages happening. And it turned out that during the whole cluster hand period, the driver is very quiet and is not producing a lot of logs. And let's do the same trick on the executor side. And you can see that during the cluster hand, there are some mild activities on the executor side. And what are they really doing? So let's zoom into it. So after zooming into the exact cluster hand period, we can try to explore the actual logs. And when you are exploring the logs, you will find that there are a lot of logs that you're not really caring about. For example, there might be some connection retry logs, or there are some timeout errors, or some heartbeat messages. During the exploration you can gradually find those patterns and filter them out so that you can find the actual Spark jobs, stages, or task activities. And after filtering all of them, we found that this whole query actually returns an empty result set, which means that no new tasks are scheduled during this time. But already scheduled tasks could be still running quietly here. So now let's do the same log message count trick just for executors during this hand period. And we can, in the visualization, we can clearly observe a pattern that repeated 3 times every 120 seconds. To compare this pattern with the actual log lines, we can later find out that these are actually executor-side shuffle connection timeout events. So later investigation revealed that a very large stage consisting of 2,000 tasks happened to be occupying all the CPU cores during the so-called cluster hand period, which means that no new tasks could be scheduled. But all those 2,000 tasks already being scheduled are actually running there quietly. They're not producing any logs, but they are burning the CPUs and doing a real work. And this makes the cluster appear to be handing. And secondly, after executor 29 got lost, other active executors will try to reconnect it to the lost executors for 3 times every 120 seconds. And these two numbers actually conform to the default values of the following 2 Spark configurations related to shuffle connection retry. And in short, this whole behavior is totally expected. It's just that the customer happened to hit a case that unfortunately met the maximum retry, and nothing significant, no significant signals got produced to indicate the activity of the cluster. And the customer thought that the cluster hand there for no good.
So now let's switch gears and look at a second case study. So in this case, a customer reported that a Spark SQL query had been stuck for multiple hours, and they gave us permissions to do live debugging on a live running cluster. So through the Spark UI, we've been able to determine that the query was almost done, and the only tasks that were still running were all in the final stage, writing out results. So now that we know that only a couple of tasks were still running, we can focus on one of them and find its executor. And from the executors list, click on the thread dump button, which will lead us to the list of threads and also their stack traces. So by looking at the thread name, we can easily find out which thread is actually running our stuck task. And in this case, it's doing a IO flush, and it's doing a asynchronously. And it's pretty easy to find the other thread that's actually doing that IO operation in a thread pool. So we can see at the bottom that this other thread is waiting on a socket read. So it got stuck for multiple hours, which leads us to thinking, are there any zombie connections involved? So by running netstat-o, we can see that one of the connections had a established off state. So now that we know that there is a thread doing network IO that got stuck, and there is a zombie connection, are these two actually related? We need some hard evidence. So for that, we can use the command line hotspot debugger to debug the internal state of our JVM. So there are multiple ways we can introspect the JVM state. We can look at its heap, we can look at its threads, and the stack frames within each thread. And usually people would start with using the JStack or the PStack commands in CL/HSDB to figure out where they are. But in this case, we want more programmatic access to the stack frames. So what I'm using here is a JS-eval command, which allows me to run some JavaScript in a string that gives me very flexible access to the JVM state. So looking at the list of threads here, I can tell that the thread in index 4 is the thread that I'm looking for. And then I can run another command that allows me to introspect all the stack frames of this thread 4. And I can see that socket read here. And then I want to know what is the state of that socket input stream. So by running this other very complicated command, I can introspect into the inner guts of this object. And I can see that there's another indirection for the implementation of the actual socket. And now here it is. So I found the socket impl object that tells me the local port is 36332, which matches the port that we saw from the netstat output. And the other interesting thing from this object is that it shows that the timeout is set to 0. And when you have a timeout equal to 0, plus there is no keep alive configured for this connection, it'll just hang there forever if the server side never responds. And we can also cross-check with GDB. So it turns out modern OpenJK implementation has this very nice integration with GDB, and then you can actually see the Java stack along with the native stack just from GDB itself. So by running GDB and attaching to our target Java process, we can run TAABT, which is short for thread all apply backtrace, to see all the stack traces for all the threads in that process. And again, we can find our thread and see this interesting bit at the bottom right, which tells us, yes, this socket read function was called with timeout 0. And that leads us to further investigation down into the actual underlying issue. But this is the very breakthrough that we needed to get to like solving the puzzle. So to recap, what we did was we used the Spark UI to identify at what stage a query is running and then which tasks are still running. So that gets us through the distributed part and down into the single node part. And then we can still use the Spark UI to get a thread dump on the executor that's running one of the stuck tasks to get an idea of what it's doing. And when a task seems to be stuck on network I/O, we can use netstat to get information on whether or not there are connections in weird state. And then to get an idea of what the JVM state is beyond what simple thread stacks tell us. So for instance, if we need to know what value some certain field of some certain object instance is, we can use various tools. And one of them that we showcase here is the CLHSDB tool that comes with OpenJK. You can also use JHSDB, which is the officially supported version since JDK 9. And we can also cross-check our findings using GDB as well. So in this case, the particular bug was actually caused by a bug inside of the JDK, and we were able to pinpoint that and then submit that to OpenJK for further fixing. All right, that's the end of our talk, and thank you so much for joining this talk. Now it's time for Q&A. Thank you.